All right, good morning everyone. This is problem number 1 on March 31st homework. You're going to see a lot of problems like this as we go through the FRQs. A lot of these little graphs of derivatives, mostly derivatives, sometimes they're second derivatives, and then they ask you to find information about the original function as well as the second derivative by looking at the picture. So this is the function of the derivative. They told us that the actual function, g at point 2 is equal to 5. So the first question was, find the points of inflection. So whenever I do a problem like this, I just think, what would I do if it was just a regular old function? You know, we've done 100 of these problems back in chapter 3. Inflection points means the second derivative has to be equal to 0. And then more than just being equal to 0, the second derivative has to change signs also, positive to negative or negative to positive. So the second derivative is, this is the first derivative, so the second derivative are the slopes. Right, so the second derivative are the slopes. So I'm just looking at the slopes of this. That would be the second derivative. So notice positive slope, negative slope. So it changed at 1. And then positive slope here. So it's changed at 4 also. And it also, you know, so it was equal to 0. There's your 0 also. So you can look at it that way. So inflection points at 1 and 4. If you're grading, wow, 3 points for that one. 1 point for the 2 answers, and then 1 point for a good explanation of what you were doing. Question 2 says, find the absolute maximum of the function. A lot of work here, pretty hard problem actually. The maximum value is going to occur when the derivative is equal to 0 and changing from positive to negative. So you notice I said here, absolute maximum occurs when the first derivative changes from positive to negative, but it also might happen at the endpoints. The most common mistake on these problems is people say, okay, the derivative, so this is my derivative, right? Derivative's positive, negative here, positive here, negative here, positive here, right? So it's changing from negative to positive. I'm sorry, it's changing from positive to negative, because that's the maximum, right? So it's changing from positive to negative right there, which is that x equals 2. This is the derivative, right? It's like if you did a little number line thing, right? We have critical points at -1, and at 2, and at 6, and it's negative, positive, negative, positive, right? So it's changing from positive, negative at 2. But it could also occur at the endpoints, and the question was actually to find the actual value, so I have to find the value. So they told me the functional value at 2 was 5, that's why I needed that. Now I got to find the other functional values. So the way to find the other functional values is to think about area under the curve. So I needed to find the endpoints. So what you see me doing here is I'm trying to find g of -3. So what I did was I integrated the derivative from -3 to 2. The reason I picked 2 is because I knew that value. Excuse me. So if I integrate the derivative, I get the function. So this is just the function at 2 minus the function at -3. But I also know that this is area under a curve, right? So the integral from -3 to 2 of g prime, there's g prime, and I'm going from -3 to 2, I just got to find the areas. These little red numbers are the areas. This is 4, it's actually -4, and -4 there. So I take that -4 area here, I take the 1.5 area here, stopping at 2, so I got -2.5, the -4 plus the 1.5. So the area under the curve I know is -2.5. And then I just do a little algebra, right? G of 2 is 5. 5 minus g of -3. Solve for g of -3. 7.5. You can also think, like the second problem you're going to see if you watch my video on the second problem, same idea, is I know I'm at 5 here, right? So the other way to just do it, you don't need the integral. You can say, hey, I'm at 5 here. This is just distance traveled, right? So this is 1.5, right? And then this is -4 again, so you can add those numbers up. So you wind up with 7.5. And then I have to do the same thing for g of 7. So I just did the same thing. You could also just look at the area, right? I started at 2. Yeah, I started at the 5. I went to the left 4, so that puts me at 1, and then I went another 1 to get me to the 1.5. So you can do it that way, or you can just integrate the same way. So the answer to this question is the maximum value is actually 7.5, because we got a 5, 7.5, 1.5. It's really easy to miss the endpoints on this problem. You forget about them. A lot of problem there. That one was worth Let me see. I think that was worth 3 points also. Yeah. One for getting each one of the endpoints and one for the final answer. So you got to kind of combine all your work there. Next part. A little bit easier, I think. That was a tricky problem for sure. The third part was to just find the average rate of change of the function. So average rate of change is just slope. So when you hear average rate of change, just think slope. So it's of g, right? So it's g of 7 minus g of negative 3 over 7 minus negative 3. These are the same values you just got on the last part of the problem. So you have to find those values one way or the other, even if you didn't find them in the last part. Here they are again, right? So 1.5 minus the 7.5 for negative 6 over 10. I think that one was just 2 points, actually. I might have an extra point here somewhere. Yeah, I might have messed up a point on one of those. 2 points for this. One for the formula, one for the right answer. And the last question was average rate of change of the derivative. So same thing, slope of the derivative, so it's just g prime of 7 minus g prime of negative 3 over 7 minus negative 3. The values are here, right? G prime of 7 is 1. G prime of negative 3 is negative 4. 1 minus negative 4 over 10, 1/2. 1 point for that, 1 point for explanation. It says, does the mean value theorem guarantee a value of c such that the second derivative is equal to the average rate of change? I remember the mean value theorem says point here, whatever that is, I'm going to get a parallel slope, but it only works, so that's what this is saying. Does it guarantee it? Normally the answer would be yes, but only if the function is continuous and differentiable. This answer is a no, because the derivative is not always differentiable. It's not differentiable at those points here, or here. So that's it for that problem. A little trickier problem. First time you see it for sure. I think you're going to see a lot of these picture graphs as you go through these problems.